Okay, so now this is a whole presentation on branch optimizations. After thinking a lot, I decided that I'll bring all of branch optimizations together into a single presentation at this point of time itself. Actually, these are distributed in different parts in the textbook. So we have already seen some parts like the delayed branches and the branch history table and the 2-bit predictor, but and static prediction. All of these are in your appendix C. And then you have correlating and tournament predictors in one part of chapter 3, branch target buffer and return address predictor in another part of the chapter 3. Since all of them, address control hazards and essentially try to reduce the stalls due to control, branches, I thought it's probably more meaningful to bring them all together into a single presentation and finish off the topics, and then we can look at other topics. So that was the purpose. And so let's look at, I just brought in the delayed branches again. So as we saw in the previous class, we can have delayed branches where we have a delay slot after the branch, right? Um, where we fill in an instruction that is always executed. If this instruction is basically an instruction before the branch, then it is very, very nice, because an instruction which occurs before the branch should always be executed, and therefore it will always be executed in the delayed slot. And therefore, we don't have any stall at all, because we are using that slot which can, where we are not wasting that slot at all, we are doing useful work. If that is not true, then we will be either, executing an instruction which is in the fall through or in the taken part of the branch. And if that prediction is not correct, then that instruction has to be converted into a no-op, essentially resulting in lost work. So, as long as we find an instruction before the branch that can be moved to the delay slot, it is the best option that we have, right? Okay. Now, this I didn't talk about in the last class. So, initially, when, long ago, when they tried to improve the stalls, reduce the stalls by prediction of branches, one of the thing they did was use what is called a static branch prediction, where the compiler predicts whether the branch will be taken or not based on the previous executions. So you have what are called as profiler programs, right? You can go and check on the Google what are the profiler programs that are available. But profiling is done very often to determine, in fact, one of the things people do to improve the execution efficiency of a program is to profile the program to see which part of the program is consuming most of the CPU time, and see how can we reduce the time taken in that particular part of the program by optimizing the code there. Okay, things like that. So the profiler program can allow you to determine whether the particular branch is taken, not taken, and based on that, the compiler can actually insert instructions in such a way that you can, do the right thing. And this allows you to reduce the stalls due to branches. Okay. While that is true, it was found that static prediction does not work so well for integer programs. and the integer programs are the ones which have a lot of branches. So they had to come up with a better mechanism, and that better mechanism is the dynamic prediction, dynamic branch prediction, which starts with the one bit predictor or the branch history table. And then it gets more and more complicated after that, right? Yeah. Did somebody have a question? Okay, so what do we do in the branch history table? We maintain a table, okay, which contains bits. If it is a 0, then it means that branch is not taken. If it is a 1, the branch is taken. This table is indexed by the branch address. Since we have 64-bit addresses today, if we say I want to address the table by the branch address, then you will need 2 power 64 entries, which doesn't make sense. So what do? You have, based on your hardware, branch history table of whatever size you would like to design. Supposing in this particular example that I'm showing, I have 1024 entries in the branch history table. So you need 10 bits to address, index into the particular location, and you so pick up 10 bits of the branch address. Normally what they do, because instructions are 4 byte aligned quantities, the last 2 bits will be 0, so those are ignored, and the third bit onwards, 10 bits are taken. If you have 1024 entries in your branch history table, and then you use those bits together to index into this table. So therefore, you will basically, be getting into the particular entry, and if the entry says 0, then you assume this branch is not taken. If the entry says 1, then you assume the branch is taken. Okay. Now, obviously, you can have aliasing where multiple branches index into the same entry in the branch history table. Therefore, the prediction will be wrong, but it doesn't matter because prediction does not always, end up being correct. And if the prediction is wrong, we basically convert the wrongly fetched instructions into no ops and continue to fetch the right instructions. Therefore, it doesn't matter, but it helps to reduce the control hazards to a large extent. That is the purpose. Now, how does this work? We initialize, because our usual strategy is branch not taken assumption, right? Why? Because if it's not a branch instruction, then it will not be, there is no taken, so you need to fetch the sequential instruction after the current instruction. If it is a branch instruction, if it is not taken, you have to execute the next sequential instruction. Only in the cases where the branch is taken do you need to fetch the target instruction. So therefore, normally not taken is the initialization that we start with. So the BHT will be initialized with all zeros in all the entries. Then you say, let's say we come to a branch instruction. So it indexes into the table, and the prediction is that the branch is not taken. But let us say the branch is taken. Since the branch is taken, the BHT will be updated to 1, saying that the branch was taken. So the next time the branch, is executed, it will look up the prediction, and the prediction will say taken. And let's assume that the branch will be taken multiple times. Therefore, all the other times the prediction is correct. Maybe if it's a loop, at the end, the branch is not taken, so there will be a misprediction at the end again. So that is the thing, and this is the FSM for the 1-bit predictor. If you are taken, it's 1, not taken is 0. So if you are in taken and it's taken, you remain in that state. But if you are in the taken state and the branch is not taken, you move to the not taken state. So this is essentially a very simple FSM that exists for the one-bit predictor. We saw the problem with the BHT that there will be two mispredictions in a loop, right? So therefore, we go to the 2-bit predictor. It's called a 2-bit saturating counter also. Why? Because we count up. Supposing you start in the state of 0, 0, okay? That is not taken, branch not taken. Now, if it is taken, so you move from the strongly not taken to the weakly not taken state. If it is taken again, then you move to the weakly taken state, or you move from 0, 0 to 0, 1 on taken. Another taken will take you to the state of 1, 0. One more taken will take you to the state of 1, 1. And there, if it's taken, you stay in the 1, 1 state. So it saturates at the value of 3, right? So this is what is a saturating counter. Now, the state diagram I'm showing here is not the same as in your textbook. Your textbook is, in the last class, I showed you the state diagram from the textbook, but somehow I'm not convinced by that. The book is very clear about it, that, you are in 0, 0 state, and if you take the branch, you move to the 0, 1 state, and if you take it again, you move to 1, 1 state. Okay. They don't talk about moving from 0, 1 state to 1, 0 state, and then from 1, 0 state to 1, 1 state. And yet they do call this a saturating counter. Now a counter cannot go from 0, 1 state to 1, 1 state. It has to go through the 1, 0 state. This is my thing, and I've looked at other, basically the Georgia Tech people talk about moving from 0, 0 to 0, 1 to 1, 0 to 1, 1 state, and I'm more convinced by that argument. So I have changed the FSM here. This is, therefore, I'm just giving you a warning that this is not the same as the FSM in the textbook. So just be aware of it, read up, and if you want to discuss about, the difference in the two FSMs, please do so. Forums are available for any discussions anyway. Email is there. All right. Now, this is where I have to restart because I don't think I have talked about this in the previous class. So the question is, if we have this 4 states in the 2-bit predictor, what should be the initial value for the 2-bit predictor? See, for the single bit predictor, we said we'll start with the not taken assumption because that makes more sense. Because taken is true only for branches, and branches make up about 20% of all instructions. Therefore, not taken is a good initialization for the single bit predictor. But what about the initial value for the 2-bit predictor? That is the point, right? So let us say that the branch has the pattern of this, and analyze what happens with each of the initial values. What I would like you people to do now is, supposing you start with 0, 0. Okay. Okay, so let us say initial value is 0, 0. Okay. Then what happens when you see T, right? You see a T, what happens? Can someone tell me? So I'm saying that the 2-bit predictor starts with an initial value of 0, 0, that is strongly not taken state. Then you see taken, the branch is taken. What will become the state of your predictor?
Weekly not taken.
Yeah, weekly not taken, which is 0, 1 state. Then you have one more taken. What happens?
Weekly taken.
Weekly taken. And then you have one more taken. So it becomes 1, 1, right? So how many mispredictions did you have now?
3.
On the first taken, your prediction was not taken, right? On the second taken, your prediction was still not taken. Okay, let me just make this point. When you say 0, 0, strongly not taken, obviously your prediction is not taken. Okay. 0, 1, weakly not taken, your prediction is still not taken. Okay, your prediction is still not taken. When you move to 1, 0, your prediction now changes to taken. Okay, so when you see T, that is one misprediction. The first T is a misprediction because you are predicting not taken and it is taken. Second one is also a misprediction because you are saying not taken and it's taken. After that, the next 3 T's, you are right because your prediction says taken. Okay. And then when you say not taken, there is a misprediction. Right? So there are 3 mispredictions for that sequence when you start with 0, 0. Can you tell me how many mispredictions will be there if you start with 0, 1?
2, ma'am.
2, right? Because you start with 0, 1, which is saying not taken prediction, but it's taken. So then you change your state to 1, 0, and therefore your prediction is T. Okay. And then you go to the end and then not taken, you have a misprediction there. Okay. The reverse pattern will be the same, right? In the sense that if you start with 0, 0, okay, there is no problem. But if you start with 1, 1, what happens? You'll have the problem, right? If you start with 0, 0 for NT, then there will be no mispredictions except at the end. But if you start with 1, 1, and this is the pattern, then you again have 3 mispredictions. So therefore, if you have 1, 1 as your prediction and you see TT, 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 and then NT, then you get a very good thing, right? What about if you have alternating T and NT? What happens with 0, 0? What happens with 0, 1? Can you tell me? So take about 6 T and T pattern and tell me how many mispredictions will be there if you start with 0, 0. How many mispredictions if you start with 0, 1?
They oscillate between 2 states. If we take 0, 0, then they keep oscillating between 0, 0 and 0, 1. If we take 1, 1, they
But
keep oscillating.
prediction, how many predictions are wrong with so it's something like this we are talking about, right? We have N, then we have T, then we have N, and then we have T. Okay. Now,
Then
if
with
we
3.
start with 0, 0, our prediction is basically N, right?
Yes.
So since we are correct, we don't change the state. Agreed?
Yes.
So the next prediction will be N from our side. Yeah,
Yes.
but it is taken. So at this point, our state will become 0, 1. Okay, our state will become 0,
Yes.
1, but therefore prediction will still be not taken. So we'll do this, right? And so on. So we don't change our state at all. However, how many mispredictions do we have? We have 3 mispredictions because every time there is a T, we are still predicting no. Okay. That is with 0, 0. Let's start with 0, 1. We predict not taken. So therefore, we say not taken. We are now correct. So we don't change our state. Okay. And therefore, we predict not taken again. When it is taken, it becomes 1, 0. So what do? We say taken is the prediction. Yeah. It says now
Ma'am,
not taken. Yeah. We
uh,
start with
like
0, 1.
if we start with 0, 1, when it's not taken in the branch, then it goes back to 0, 0 number, according to your right?
No, 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 no. Why should it? It's okay. I think you're right. Okay. So it will be basically not taken here. And okay, here is the thing. You start with 0, 1, right? Okay. And maybe I should do the reverse. If I start with taken, not taken sort of pattern rather than this.
Yes.
Let's do this. 1. Okay, we start with the taken, not taken pattern. Okay, then we start with not 0, 1, let us say. So we predict that it's not going to be taken, but we are wrong. So it goes into 1, 0 state, right? Our prediction is 0, 1, but the branch is taken. So it goes to 1, 0 state and predicts that the branch will be taken. Okay. But the branch is not taken. So it again moves into 0, 1 state, which is basically predicting not taken. So this is what a single prediction will be wrong in this case. This is the worst case that can happen when you have an initialization of 0, 1 and you have alternating T and NT, then every prediction can be wrong. Okay. So in fact, for any 2-bit initialization, you can find a pattern of branch behavior, which will result in the worst case of every prediction being wrong. Okay. So that is the lesson we need to take from here. And so starting with either 0, 1 or 1, 0 is good for the more common patterns of T, 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 and finally NT. or an NTNT and so on. But this leads to the worst case performance of misprediction every single time for the alternating pattern of TNT, TNT. Okay, this is what we need to understand about the initialization of the 2-bit predictor. So which value makes sense? For the regular common, loop behavior, because loop behavior will be either all taken and then at the end one not taken, or all not taken and at the end one taken. The 2-bit predictor initialization will be good to have 0, 1 or 1, 0. Either of them will work fine. But if you have alternately taken, not taken sort of a branch behavior, then you will be having a wrong prediction every single time. Okay. So that's something we need to keep in mind. And we will see in the next class why branch prediction is so important and why you have more and more complicated branch predictions that are implemented in the modern processors, and all the other optimizations that are done to reduce the stalls due to branches. Okay, any questions on anything we have covered? Please send mail or set up, ask in the forum. Okay, all right. Bye then.
Thank you.
Thank you.